Okay, so systems of equation with elimination. The nice part about this is that it's a very orderly way to do everything. You notice on all the substitution ones that we had, we start getting equations going off on the side, and you can follow them, but there isn't a nice progression of steps that we're taking. So with elimination, we get to keep things kind of together in groups. And that should help us a little bit stay organized, especially when we have more than two variables. So what I'm going to do is I'm going to take this little example down here, this 2x plus y equals 3, and the x minus 2y equals negative 1. And so I'm going to lay out the steps that we're going to use for elimination and then perform them on the bottom on this example. Okay, so the first thing that we can do with elimination is that we're going to multiply one or both equations to get one of the variables to have the identical coefficient except being the additive inverse, okay? So what this means is I don't have any coefficients that look like they're the same here. So what I'm going to do is I'm going to, in this case, multiply the first one by 2. Okay, so if I multiply the first equation by 2, I get, 2 times 2 is 4, 2 times 1 is 2, and 2 times 3 is 6. So this first equation transforms into 4x plus 2y equals 6. And my goal here was that I picked some equation so I have a 2 in front of the y and a negative 2 in front of the y on the other equation. I could have easily picked this second equation and multiply this by negative 2. That would have given me a negative 2x in the second equation, which would be the additive inverse to that 2. So since I already had a natural negative and positive built in here, I chose the first equation, multiply it by 2, and so now I have these two equations where the 2y and the negative 2y are nicely lined up. So then the next thing I want to do is I want to add the two equations together. And this eliminates that one variable, and this is why it's called elimination, is because we're going to be multiplying and adding equations to get rid of certain variables that we choose. Okay, so what I do is I take my two equations here, and I'm going to add them together. So I get 4x plus x is 5x, and then I'm going to get 2y minus 2y is 0, and I'm going to get 6 plus negative 1 is going to be 5, and so I have 5x equals 5, and of course then x equals 1 drops right out. Now to get the other variable, the y, what I do is I just substitute it back into whatever equation will make my math the easiest. Okay, so in this case so let me write that out. One of the original equations to solve for the other variable. Okay, so I'm going to choose that first one and say, well, if my first equation says 2x plus y equals 3, I already know what x is, so I have 2 times 1 plus y equals 3, and so I have 2 plus y equals 3, subtract 2 from both sides to get y equals 1, and so my solution is 1, 1. And I can check that by putting this back in here, so I have 2 times 1 plus 1 is 3, that's good, and then I have 1 minus 2 times 1 is negative 1, and that one's good too. So there's my system. Now this perhaps doesn't seem too different than substitution, and for two equations, two unknowns, it really isn't that different, okay? You'll find that a lot of the arithmetic that you do is about the same, but when we get into more equations, this is going to really keep things organized. But let's stick around with this one a little bit. Okay, so we check the results. Now, if we get something like no solution, we're going to get that same kind of thing where instead of something that can be solved like 5x equals 5, we're going to get some variation of 0 equals 1 or 0 equals negative 2 or something that just can't be, all right? Then we know we don't have a solution. If we get 0 equals 0, which is true all the time, then we know we have infinitely many solutions. So if you end up with something that doesn't let you get a single x or a single y, you either have no solution or infinitely many. if what you end up with makes sense, that means you have infinitely many solutions. If you end up with something that can't be, like 0 equals -1, you have no solution. All right, and there's my check. Okay, so let me go through a couple examples and I'll have you do a few as well. So here's one, 4x plus 3y equals 8 and x minus 2y equals 13. Nothing really jumps out at you as maybe favoring the x or the y in this case. So I'm going to multiply both equations by something. Now, I notice I have a 3 and a -2 here, so this looks really good. If I multiply this first one by 2, I get 8x plus 6y equals 16. Multiply the next one by 3, so I get a -6, so I get a 3x minus 6y equals 3 times 13 is 39. So now I have these two equations, and they're in a perfect spot for me because I have a 6y and a -6y. So when I add those two together, 8 plus 3 makes 11x, and then 16 plus 39 is 55, so I divide both sides by 11, and I get x equals 5, and then I'm going to substitute in, and I get, sure enough, I get y equals -4, so I had 20 plus 3y equals 8, then 3y equals -12, and y equals -4. So there's my solution. Always write it as a pair, an ordered pair like that, and then check your solution, and that works. Now remember, with absolute value inequalities, we would get sometimes where everything would be right, but then you check it and it would be wrong, and it wasn't because you did anything wrong, it's because there was no possible solution. You got an extraneous solution there. And that's not going to be the case with two equations and two unknowns. Is that if it doesn't check out, it's because you made a math error. Okay, so if you end up with something that can't be, you have no solution. If you end up with something that's always true, it's a solution. If it looks like you got a solution and you put it back in the equations and it doesn't work, you've made some sort of error. Okay, unlike with the absolute values where it's very well possible that it's an extraneous solution. These, you won't have extraneous solutions. Okay, so let's look at a different one. Let's increase the difficulty a little bit. All right, so here I have 5/3 x plus 3/2 y equals 11, and 1/5 x minus 2/3 y equals -31/15. Okay, now there's nothing that says that you have to jump into elimination right away. Just like when we were handling these for any other purpose, you can eliminate the fractions first and then start with your elimination. So I'll do that. Multiply the first one by, get a common denominator of 6, and so I multiply 6 times 5 divided by 3, and I get 10. 6 times 3/2, the 2's cancel, and so I get just 9y equals 66. The second equation has a different common denominator, it's 15, and so I'm going to multiply the whole thing by 15, and I get 3x minus 10y equals -31. Okay, so now I have my equations with integers, and this is always a good thing because integers are easier to deal with. So at this point you think, where do I go from here? So I want to make something that's going to eliminate, so I can either choose, well, I can go back into fractions if I want and multiply the second one by 10/3, but that's not going to really work. So I'm going to multiply both equations by something that'll give me something in common, and it looks like probably the easiest one will be multiplying the first one by 3 and the second one by 10. So I get 30x plus 27y equals 198, and then I'm going to multiply this next one by -10, you see, so I get my -30x plus 100y equals 310. So you got to be really careful to keep consistent with your positives and negatives. Like this used to be a negative, now it's a positive because I multiply it by -10, and the -10 times -31 is positive 310. So it looks like it's getting messy, but it's not too bad. We'll add these two together, and we get 127y equals 508. And so 508 divided by 127 is 4. So nice, we got a nice integer. And then We don't have to go back to the original equation to figure out what x is. What we can do is we can look for whatever equation looks like it'll make it easy for us to solve for x. And so in this case, I'm going to take the second equation after I've eliminated the fraction, and I'm going to say, okay, I'm going to put my 4 into here, because that gives me 3x minus 40 equals negative 31, and so I get 3x equals 9, and so x equals 3, and I get my solution as 3 comma 4. Now at this point, if you're going to check, you probably should go back to the original equations to make sure that you didn't make any mistakes along the way, because if you made a mistake translating this into here, and if you use these to check, you're never going to catch your mistake. So you really should go back and check the whole thing. Okay, so here's a couple for you to try. Actually 3. So I'll let you work with those for a little bit. Okay, so then just to keep us up here, in the notes I have this all, and you can see I got the same solutions as all of you on the board, and I checked both equations, so you can refer back to this if you look back in the lecture notes or so, if there's any questions. Okay, so let's look at a rate problem now. I'm going to have a couple examples of some word problems that we're going to set up with 2 variables. And sometimes it works better with 1 variable, sometimes it works better with 2, and largely it'll be up to you whether you want to make 1 or 2 variables, but I think we need to talk about how to do it with 2 variables if we choose it that way. Okay, so a plane is flying at a constant speed with respect to the air. Okay, on a 3,000-mile trip, it takes 6 hours, 15 minutes one way and 5 hours back. What was the plane speed and what was the constant wind speed? Okay, so in one direction, the wind is helping the plane move on, along a little faster. On the way back, the plane is flying against the wind, so the speed with respect to the ground is less. All right, like all good word problems, we draw a picture, label it. The combined rate times the time is the distance. So the combined rate, by combined rate I mean the wind speed and the plane speed times the time equals the distance. Okay, so if we have p as the plane speed and w as the wind speed, so those are logical variables that we can set up, we set up the 2 equations that we're working with. P plus w times 5 equals 3,000. P minus w times 6.25 is 3,000. So in this first one, we're saying the plane is flying with the wind, and you know that that's a faster speed, and so it takes a shorter amount of time, equals the distance. The second one is the plane is flying against the wind, so it's the plane's speed minus the wind speed will give you the speed with respect to the ground. Then times 6 1/4, that's 6 hours 15 minutes, equals 3,000. Now there's two ways to solve this, and the way I solved it I think was the long way. So let me first show you the long way, and then we'll discuss the short way. But in essence, well, let me just take you through this then. Okay, so I'm going to distribute the 5 and distribute the 6.25 and multiply the 6.25 times 100 so I don't have any decimals. So I have 625p minus 625w equals, looks like 300,000. So I'm going to see what does it take to get up to 625 from 5. And so I'm going to look at the ratio. And since I know I'm going to have to multiply this top one by 125 to get to 625 to eliminate this. So 5 times 125 is 625, 5 times 125 is 625, and then I have 125 times 3,000 is 375,000. Okay, so then I'm going to add these two together, and I get 625 plus 625 is 1250p, the w's eliminate, and then I get 675,000, and now I'll do a little bit of division, and I get p equals 540, and then I'll substitute that into one of my equations, and I solve for w, and so I get my wind speed is 60, and I'll check that with both my equations, and that checks out, so I'm good there. And my answer then is the plane flew at 540 miles per hour, and the wind blew at 60 miles an hour. So the key step here was to get this 5 times 125 up to 125, so I have these two equations to work with and eliminate this. Now there's a little easier way if you look at this up here. If I have p plus w, if I divide both sides by 5, I get p plus w equals 3,000 divided by 5. Okay, and then I'll do p minus w divided by 6.25. And that's actually not too bad if I do that division. So I'll say 625 divided by 3,000 with 2 more zeros. And so here I'm going to have, what is that going to be? 4, so there's a 2, 8, 10, 24, 25. And so then at this point it'll be 8. 8 times 5 is 40. 16 and 4 is 20. 50, so this is 480. So my two equations would be p plus w equals 600 and p minus w equals 480. And that of course would be a lot easier to do, because when I subtract I add these two, I get 2p equals 1,080. And so then 1,080 divided by 2 is 540, so I get it much faster. So sorry for all the math. This is a little easier this way. And it doesn't matter. You know, you can manipulate these equations any way you want to get to two things that eliminate. And that's probably way easier than what I showed in the slide. Okay, any question? The main point of this is just basically setting up the two equations with two unknowns with what you need, and then solve from there. Okay, so let's look at a mixture problem. You've done mixture problems with one variable, and you'll see the similarity on this one with two variables if you decide to do it this way. And so let's say we have how many liters of a 40% alcohol solution should be mixed with a 65% solution to make 20 liters of a 50% solution. All right, so we're going to say A is the number of liters of the 40% solution, and we're going to say B is the number of liters of the 65% solution. And so we can make two equations with this now. We know that the total amount of A plus B equals 20. And then we also know that 40% of A plus 65% of B equals 50% of 20. So from here, I can just multiply by 100 and get my 40A plus 65B equals 100. Now notice what I can do. I'm setting this up in two different ways. And this should stop here. Oop, I want it to stop. Stop. Okay, so here I have this equation, this 40A plus 65B equals 1,000. Then I'm going to say from this, where I know that B equals 20 minus A. And so by substitution, this equation should look really familiar in form. That's just the way you did mixture problems before, you know, with one variable. You did the substitution in an implied basis. Now, with elimination, here I'm retaining these, and I'm going to solve both of these by multiplying probably that first equation by something to eliminate either the A or the B. So if I do the math on the first one, I get A equals 12 and B equals 8, okay, just by solving this substituted equation, right? 40A minus 65A is negative 25. Subtract 1,300 from both sides and I get negative 300. So I have A equals 12, and then put in this first equation, if I know if A equals 12, B must equal 8. By elimination, I'll multiply that first equation by 40, and I get essentially the same answer. So what happens here is I've multiplied this first equation by negative 40. So I have negative 40A minus 40B equals negative 800. Add these two equations together, and so I get 65 minus 40 is 25B equals 200. B equals 8, and then with the same computation I get, with the first equation A plus B equals 20, I get A equals 12. So same answer, arrived differently, but nevertheless it's an alternate way to do it from the way that we got with one equation. And the advantage to this, of course, is that it generalizes into having many more equations and variables. So with two equations, two unknowns, there's lots of ways to do it. With three equations and three unknowns and more, we're going to find elimination is way more organized than substitution. Substitution, you're going to have to make lots of substitutions. With elimination, you still make a lot of eliminations, but they stay pretty well organized. Okay, so let's talk about more variables now. What this will look like is we keep this kind of traditional structure where we're putting all the variables on one side, and just for the lack of any better reason, we put them in alphabetical order, and then we put the constants on the right sides of the equation. And so you think, okay, how are we going to solve this? And we're going to just touch on this today, and we'll be dealing with more of this on Wednesday. Okay, so your homework is only going to consist of two variables, two unknowns. But this, I want you to look at this just to get you thinking about it. We're going to make an effort to transform this into a form that looks like this, where we have three equations, or three variables, two variables, and one variable, and that's going to be called row echelon form. So the rows are going to form an echelon where we have 3, 2, and then one variable. And then when we have it in this form, since we know what z is in this case, we can solve this by saying, okay, if z equals 1, then I look at the second equation and I put the z in there. See, this 3y minus 1 comes from this 3y minus z, and since I know z equals 1, I can pop in my 1 here, and I get 3y minus 1 equals 2. Add 1 to both sides, 3y equals 3, and y equals 1. And then I do the same thing with the top equation, where I'm going to say x minus and I know y equals 1, so I'm going to put a 1 there, and I know z equals 1, so I'm going to put a 1 there, so I get 3 times 1 equals 5, and so I'll have x minus 1 plus 3 equals 5, x plus 2 equals 5, and x equals 3. So then my solution here, I can check it back in my original equations, and I'll end up with exactly the same thing. My solution is now going to be a coordinate triple, or an xyz point. So imagine this rather than on a plane, this is in space now. Okay, and so what the equations represent are planes and not lines, and what they're but still 3 planes that aren't parallel will all intersect at one point. Okay, so this is row echelon form, and this is what we're going to be going for. So there's the first part of this is that we're going to look to see what do we do. Well, I've just shown you what we do once we get row echelon form, that we can find the solution like this. After we talk about that, I'm going to talk about how do we get equations that look like this into row echelon form. Okay, so it'll be 2 steps. And actually, why don't you try this, and this will be kind of the way that we're going to finish today. So here's a row echelon system of equations, and I'd like you to figure out what x, y, and z are. So you know what z is, figure out y, and then you'll know y and z, figure out x. All right, so this is called doing the back solve. Okay, so this is kind of the second half of the process. We'll come back to this on Wednesday, and we'll learn how to do the front part of the solution.